So what do we have? We have structure and bonding, yeah, functional groups, hybridization, all that good stuff. DUS, charges, you have it all. Then we had what? Physical properties, yeah, including what was that? Melting point, boiling point, solubility, polarity, yeah. Acid-base chemistry, good bit there. And we have conformations of alkanes, some miscellaneous things there, but Newman projections, chair conformations, that type of stuff. Nomenclature of alkanes, cycloalkanes, yeah. And IR. Test is similar format to quizzes, short answer. There will be some multiple choice. And there'll be IR, like similar to the IR problems in the workbook. Any questions about the test on Wednesday? Any questions, last questions about the material? All good to go?
Yes, sir.
Yeah.
So, drawing the both conformations and cycloalkane, if two atoms are like, let's say, cis, right? Do they both have to be axial or both have to be equatorial, or something?
No. Well, you said both. Typically, chair is a better conformation.
Yeah, chair.
And we've not drawn a boat.
So like when you're drawing a chair conformation and you have let's say two atoms like right next to each other that are cis, so like they're going away from you, would they both have to be on the axial or equatorial, or can they change, or can they be on one on the equatorial and one on the axial?
I mean, no, they can't change unless you want to change them to trans.
So they both have to be equatorial or axial?
No. Well, it will depend, yes. But that's not how you look at it. You look at it if the how it compares to the H, groups up or group down, right? Yeah.
Yes.
Is that how we did it?
Yes.
Is the group above the H or below the H? If the answer is the same, then they're cis. If the answer is they're different, then it's trans. Has nothing to do with them being axial or equatorial. Two groups can both be axial, they might be cis or trans, depending on where they're located. Now we can memorize every possible position. If they're next door to each other, then if they're both cis, then that's too much. All you gotta do is remember, is it up or down compared to the H? If that's the same, they're cis. If that's different, they're trans. Now folks will tell you a variety of ways to do it. I don't know, but that's the way I'm recommending you do it. If you do it that way, you'll get it right 100% of the time. Right? Yes. Other questions? If there's no questions, we'll begin test 2 material. Going once. Twice. Okay, seems like we're good to go. I was expecting lots of questions. We'll move ahead though. Test 2. Any questions about lab this week? We're doing recrystallization, is that right? Okay, there's a video for recrystallization. Question?
What if we don't get enough thought, like, for a crystal? Or what if we do, but then it dissolves back again while we're moving it?
That's not going to happen.
It's not gonna happen.
Why would that happen?
I don't know. I was thinking maybe like you're moving the glass to the kind of things that maybe.
Okay. Thank you. Lab report for the unknown, we'll say it will be due on Monday, a week from today. Okay? Need to get test taken care of this week. Need to get lab done. Yeah. Okay. Be due here in class. Okay. Test 2. Test 2 is over reactions of alkenes. Lots of reactions. Also reactions of alkynes and stereochemistry, including chirality. Okay? I may send some handouts to you by email so you can have them, and I may ask you to print some of them, but to get them to you as soon as possible. Because test 2 is on a certain date and it will be here at some point. All right? But I'm giving you one more day on the test, but we're going to begin new material. Before we get into reactions, we need to do a little review of thermodynamics and kinetics. And largely, you've seen a lot of this, but we'll put it in the context of organic chemistry. Okay, let's move through this. Again, a lot of review here. There are two reactions there. Decomposition reactions. NF3 will decompose to nitrogen gas plus fluorine. I balanced those reactions there for you. I must have been delusional or something. I don't know what happened. But I balanced them. Bond strings. Here's some questions about those reactions. Which reaction gives off the most heat or energy? Of the two up there. Which reaction is endothermic? Which will occur fastest? Are the reactions driven by entropy or not? Those are some types of questions you should be able to answer about reactions. If you can answer all those, we could maybe end the lecture right there. Are you good to go, or would you like to review this material?
Review.
There's some more bond strengths down there. Okay. For the model reactions, I had to give you some bond strengths because they're not in the table. Okay, first off, line reactions. May have used this term before. Hopefully, maybe you've used this term. A line reaction basically shows a reaction has a reaction arrow. It can look like this. This reacts with this to yield this product. Sometimes we can put a small reagent actually on the reaction arrow. So this is looking like this reacts with HBr to yield that product. Same as above, except we put a reagent on the arrow. Very common. Okay? Also very common to do it and include conditions, maybe temperature and time. Okay? So this would be more a very typical line reaction here. Now a single line reaction may also show multiple steps. For example, this alkene reacts with HBr to give some product. That was one. One happens 1 week. Next thing happens next week. These are not mixed. Okay? Not mixed. And after reacting with one, there's some product that is not shown. Maybe that's it. But then that reacts again with something else to give the final product. Two separate reactions. We're not showing the product after reaction one. You could have 1, 2, 3, 4, 5 and go from here to here. Okay. Thermodynamics, you know what thermodynamics is. Equilibrium. Gibbs. We can work our way all the way down to summary of Gibbs free energy equation, yeah? Delta H What is H? Enthalpy. Okay. Heat. Our bond strengths are going to give us a look at delta H. And then delta S. Entropy. And temperature magnifies the entropy term. Okay. I believe it was Josiah Gibbs who developed this equation. Yeah? Who, by the way, I believe, was the first person in the United States to receive a doctorate degree in science in the 1800s. Yeah? I believe from Yale University. Y'all familiar with Dr. Gibbs?
No.
You've never seen the Gibbs free energy equation?
We have, we just don't know about that.
It's not the main.
You didn't know about Dr. Gibbs, then?
No.
Okay. Should be largely review. I'm not going to review it for you. You need to review it. You need to work with it. Again, delta H is going to be directly related to bond strength. That's why we have tables of bond strengths. Okay? Positive or negative? Which one is favorable? Negative, meaning reaction will be exothermic. Okay? Exothermic is favorable. All right? That would be negative delta H. The negative meaning the system has lost. Negative meaning lost. The system has lost energy. If this loses energy, that means it's released. Negative. Delta S entropy. Which is favored there? Disorder is favored in nature. That would be positive because it's disorder. We say the system has gained disorder. It's almost like a double negative, but it's positive is favorable there. Delta S examples first. A, alkene reacting with HBr. I think that looks like previous page. Delta S is negative, meaning the system has lost disorder. That means it's gained order, right? How has the system gained order? Going from two molecules combining to make one, we're getting more ordered. Okay? And so we would expect delta S to be negative. We're just doing a qualitative assessment of reactions, and this is a couple of examples. Let's do the opposite here. What if this converts to those two, and I showed it this way? That converts to those two. By the way, this is called an addition reaction. These two add to make that. This is called a decomposition reaction. Or you could call it an elimination. Here, one molecule is going to two. That is an increase in disorder. So for the second one, delta S should be positive. Yeah? Spontaneity, is that right? Which reaction, A or B, is favored by entropy?
B.
B. So if a reaction is being controlled by entropy, this is more favorable. That is, if we look at this, just look at A, is the forward favorable or the reverse? Reverse, that's what B is. B is the reverse of A. Okay? So the reverse is favored by entropy. What about enthalpy? We'll have to do bond strength calculations there. And then the overall answer, delta G, comes from the two terms, enthalpy and entropy. Sometimes the two terms will reinforce each other and give you the same answer. Sometimes they will conflict. That is, sometimes a reaction may be favored by entropy, but it's not favored by enthalpy. So what's the overall answer?
It's
The
free
equation.
energy.
Yeah, but what's the overall answer if one of your terms is favorable and the other is not favorable? It can sometimes be difficult to determine. Okay? We're going to look at each individual term. We're not going to look at the overall term too much. Right here we're looking at the delta S only. How about this next reaction? What if this reaction, make this ring, it cyclizes?
Delta S.
Is delta S be expected to be positive or negative?
Negative.
Negative.
Why negative?
Because it's forming a structure. Because it's forming a structure.
Because it's forming a structure?
It's forming a ring.
Yeah, but why does that make it negative?
It's like it's going from less order to more order. So it has to create a bond. It has to create a bond to form the.
Did you say more order?
Yes, sir.
I thought you did. Did you?
Yes, sir.
Okay. Yeah, it actually is more ordered. This has lots of free rotation, okay? All these groups can just do whatever. Once it makes a ring, it limits the rotation. And it's more ordered when it makes this ring. One molecule going to one, you can't answer that. This is easier. Two going to one going to two. This is 1 to 1. The more order comes from, because it's a ring, it has less ability to do all this. So yes, typically making rings is not favored by entropy. So those are a few examples. Delta H. By the way, we did not quantify anything up here. We just assessed it qualitatively. Delta H we will quantify using bond strings. This alkene plus HBr, very similar to above, except we don't have the methyl group on this alkene. Do this additional reaction to give an alkyl bromide. What would be delta H? We need to look at what bonds are broken. The pi bond is broken, it's gone. The pi bond is worth 63 kcal per mole. That's the bond strength. It's the amount of energy it takes to break the bond. What else is being broken over here? The HBr bond is being broken. That is 87. Were those values in this from the table? HBr 87. Okay. Typically, we'll use kcal per mole. And what was the other? Alkene?
Carbon. That's not there.
Carbon-carbon pi bond? What was the answer? Was it 60 something? 63. Well, what is this? That looks like it there, 174.
That's the sigma and the pi bond.
How do you know that?
Because there's a hydrogen combines the carbons and there's pi bonds.
You said that?
No, you said it.
How do you know it's the sigma and the pi?
You can see the pi bond, but it's because the sigma bond between the hydrogen and the carbon, so you have to combine those together. The pi bond is one pi bond and a sigma.
And a double.
Well, I agree with all that, but how do you know that this is referring to the sigma and the pi, not just the pi? To me, it's a little unclear. You seem pretty confident that it's referring to both.
Potentially.
Okay, we'll move on. The answer is it is referring to both. The pi bond itself I gave you, I had to get from another table. Okay? And so 150 kcal per mole broken. What is formed? A CBr bond is formed. Everybody agree? It's not over there. 69, is that in the table? Because some of these values I may have gotten from a different table. I don't want you to get confused if the value is different. CBr?
The primary CBr bond is 72 in our table.
Also, you see the bromine is on different types of carbons. A methyl, a primary, a secondary, or a tertiary. You see that? Right? You see? Primary, secondary, tertiary. We understand substitution of carbons. What was the value on the other page, 69? Yeah. What type of CBr bond are we making in the, is it
Primary.
primary? So primary carbon. So here it says 72. Yeah. You can mark that out and put 69 just so we're consistent. I got some values from a different table. And sometimes tables will vary a little bit. Okay? Okay, so that was broken, this was formed. What is delta H?
Negative 20.
Negative 20, right? Why is it negative, not positive 20?
Reactor minus product.
Okay, but what does that mean, though? That sounds like a memorized math equation.
It's broken minus Baltimore.
More energy was released than it took to break the other bonds.
Do what?
More energy was released in the forming of those bonds than it took to break the bonds in the product, or in the reaction.
Yeah, I would rather you have some explanation of why it's that, not just that you did some math. Okay, here we go. Here's my explanation. These are bond strengths. Which bonds are stronger, the ones we broke or the ones we made? Made. We're making stronger bonds. And stronger bonds typically means lower energy, more stable, lower energy. This side is now lower energy because it has stronger bonds. Well, energy can't just disappear. If this is lower energy, where's that other energy that was on that side?
You have to add it to the product side of the reaction. And heat, maybe?
If this side is lower in energy, where's the other energy? The energy over there has to equal the energy over here. Not necessarily the molecules, but just that side's higher energy, this is lower. Where's the other energy?
In the universe.
It got released. So that energy over there equals this energy over here. But the molecule contains a lower amount now, because it has stronger bonds. So where's their other energy? It was released. It didn't just disappear. It left the system, because that's the system. And if heat leaves the system, delta H is exothermic, delta H is negative. By how much? The difference in the numbers. It's negative 20. Okay? Okay, so it is negative 20. Yes, you can do, what is that? Reactants minus products? Is that what it is? See, I don't even know what it is because I don't do that. I look at which side's more stable, and that should be exothermic. Okay? That way you don't get confused if someone kind of manipulate the formula or something. You understand fundamentally what is going on. Okay, that's a favorable reaction. Let's go back and look again. So that reaction is favorable by delta H. Everybody agree? Favorable by delta H. What about delta S? Is this reaction favorable by delta S? No, because two molecules going to one. So as you see, we have conflicting answers. Favored by delta H, not favored by delta S. What's the overall answer?
Do we need to know temperature?
Do what?
Do we need to know temperature to know the answer?
Yeah, go ahead, tell me.
High
See,
temp-
you guys may know more than me. You're looking at doing an actual calculation.
high temperature.
But what is delta S?
You said it was
Entropy.
Yeah, but if you do that calculation, what is delta S though?
oh, we don't have a number for it, you're saying?
You said you need to know temperature. Temperature to multiply by delta S?
Correct, but we don't know delta S is what you're saying.
So so how are you going to do that if you don't know what delta S is?
You know it's delta S is negative since it's unfavored. So you can make general statements about the temperatures.
Negative is positive, so
You can say that at high temperatures the reaction is favorable, but at low temperatures it's not.
yeah, negative is first, negative is
Because a negative.
Okay, let's talk about delta S. Delta S for this is not favorable?
No.
Not favorable, because two going to one. So we can say this about temperature. If you want this reaction to happen, would you want to heat it high, or is that a good thing to heat it, or is it bad?
High temperature.
Yeah.
You wanted a low temperature.
Oh,
you don't
Yeah, it'd be
Yeah,
better
yeah,
for
yeah.
this reaction. Lower temperature better. Heating this reaction is not going to help it. It may help it in some regard to do activation energy, but at some point heating is going to be bad for this. Because temperature magnifies the delta S term, right? And if delta S term is bad, heating it is going to make it overall bad, bad, bad. Okay, calculate delta H for the following reaction. Tell the reaction is exothermic and endothermic, favored or disfavored. Okay, this is just another example. What bonds are broken over here? If I agree that CH bond is broken, and the F2 bond is broken, yeah? What's the tertiary CH value? Everybody got it? Front table? Is it 97 kcal per mole? Yeah? F2? 38? Is that right? 5? Was that 135 kcal per mole? What's formed over here? Tertiary CF? The only CF in the table is just a methyl F. 115? We're going to have to use that, because, I mean, unless we find another table. Yeah? CF is 115. What else is formed? HF? Is that in the table?
Yes, sir.
136? 136, what is this? 251? Is this reaction exothermic or endothermic?
So
We're making more stable bonds. Lower in energy. What is delta H?
negative.
Negative what? 116? Is that right?
Yes, sir.
Try to do math there. Is it negative?
Yes, sir.
That's fairly exothermic. That would be expected if you know fluorine chemistry, because things react with fluorine pretty exothermically. Okay. Fluorine tends to be a very dangerous reactant. Mainly because the F2 bond is very weak. Look at that very low number compared to most numbers. Very weak, but it makes very strong carbon-fluorine bonds. So because it's making very strong bonds, it tends to be very exothermic. Yeah? A reaction would be very favored. In terms of entropy, entropy is kind of a wash, 2 molecules going to 2. You tried this down here yourself. Try with I2. There's a couple for you to do on your own. Kinetics. Rate of the reaction. A reaction can be favored by thermodynamics, but actually not take place. Because the rate may be so slow that it's just almost zero. Essentially is zero. A diamond in a ring reacts with oxygen very exothermically. Does that mean it's going to happen just readily? No. I mean, diamonds don't, there's oxygen everywhere. A diamond just doesn't just react. Because the kinetics is slow, so slow. And what dictates kinetics? Largely activation energy. Okay? Like that up there, that's a very exothermic reaction. It doesn't necessarily mean it's going to happen. If the activation energy is too high, it just may not happen. Okay, we need to be able to understand reaction coordinate diagrams. Several here. Some type of energy. Usually I'll just kind of say E over here. It can be very generic. Reactants. Reaction progress. Charting the energy. This shows products. It shows it is exothermic. Okay. Now, this says delta G. I would probably say delta H, okay, to make it more specific for delta H. So, it doesn't have to be delta G. They're focusing on G, and if we say delta H instead of saying exergonic, I would say exothermic. I would stick to delta H terms. So this shows it's exothermic. This would show a reaction that is endothermic. Okay, the products have gained energy. What is this right here?
Energy of activation.
Yeah, that's the energy. That's the activation energy. Okay. The amount of energy it takes to do the reaction. What is? This is reactants products. What is formed up here at this high energy level? That is the transition state. Okay? Somewhere between when things are reacting, okay, we're going to react. How do we just stop? Do we just go products? No. Let's just make a bond. Can we make a bond? Oh, I saw you move your hand. That took energy. Right? Here we go. I'm using energy. I'm using energy. Now we settle back down. Okay. Here we go. I'm raising my hand. Oh, we're making hands. Okay. It's that transition state where bond is being made. All right. Sometimes call it activated complex. All right. The molecules had to have some energy to do that magical bonding thing. Which reaction most favorable of these four?
First.
Okay. Exothermic. These top two are exothermic, yeah. Bottom two endothermic. Which one is most favorable?
A. The first one.
It all depends on what do you mean by favorable.
Least
In the
activation
forward
energy.
direction.
In the forward direction and takes the least amount of energy.
It's hard to tell, but I think that that's more exothermic. I'd say B is more favorable. Most exothermic, yeah? I would use favorable as a thermodynamic term. Which favorable reaction is fastest? The top two are favorable, they're exothermic. Which one's going to be fastest?
The first one.
A, because rate depends on transition state energy, activation energy. It's like if you live over here and you want to go to grandma's, okay? What's going to be a faster trip to grandma's, going over this little mound or this huge mountain? Much more difficult climb. It's going to be faster. None of these reactions here show intermediates. All we have is just one transition state. There's no discrete intermediate. Down below we have an intermediate. These two react, okay? We have a transition state here, yeah? This is the activation energy. We fall into some intermediate well. Okay, energy well. In this case, it's a carbocation. A charged intermediate that is formed. Then a second reaction takes place, and we get the final product. And so we have another transition state. And this would be the activation energy for the second step. Since we have two steps, we can say, which one is the rate determining step?
The first one.
The first one. One with the highest activation energy. It's going to dictate the rate. The most difficult step dictates the rate. So this would be your rate determining step. This over here would be called the fast step. Yes?
From going from the intermediate to the second transition state, would the activation energy still be from the bottom line or from the intermediate one?
That's a good question. You just want to have it right there. Actually, I've thought that before. Which do you think it is?
I believe it's the second.
You believe it's the second one? Anybody else know the answer to that?
Well, for the second one, it should be higher up, right? Because you're not starting from the bottom. Now we're here.
I actually don't know. There's reasons here, because there's got to be some energy here. It's almost so-called semantics to me. I mean, the system has to be existing at a certain energy level here. It's whether or not you call that baseline and I haven't had Gen Chem in a long time, and I've often wondered about this.
It's not a change in
There's
it's asking for activation energy itself.
when
It's not a change in activation energy, it's asking for the activation energy itself. So it'll be the whole.
so she says the whole thing. You say just the upper part. Y'all think about it and let me know. Okay. What's clear for us here is that the first step is the greatest activation energy. The first step in this example is the rate determining step. The second step is going to be fast compared to the rate determining step. Now, please let me know if you want to. What else can we say here? Two transition states. This is an overall reaction, and sometimes you may have heard the term elementary steps.
Yeah.
Two elementary steps in the overall reaction mechanism. First step is forming the carbocation. The next step is reacting with the Br minus with the carbocation to give the carbon-bromine plus. Two elementary steps, each with their own activation energy. On the back here, what do we have? This illustrates something that we will mention several times. Two different intermediates, okay? We're not continuing on, it's just going to here. We will say that the lower energy intermediate typically has the lower activation energy leading to it. Higher energy intermediate has a higher activation energy leading to it. We call this A and B. Okay? If we're starting at the same point and we say, hey, this can go either to A or B, which one is it going to prefer? A. Why?
It's more stable.
Right. The answer is not because A is lower in energy. The answer is because the activation energy leading to A is lower than the activation energy leading to B. That's the answer. And if that's your answer, you will never be wrong in your assessment. If you just look at A and B, you could be wrong sometimes. Okay? But we're making the assumption that a lower energy intermediate has a lower activation energy. And that's a common assumption. But there are exceptions, right? By the way, this shows A and B are two different here. That's B, that's A. It's a carbocation. We should know why that's more stable, right? How do you stabilize a positive? Electrons towards it or pull away?
Pull away.
You stabilize a positive by moving electrons towards it, correct? Okay. That's the answer, why one's more stable than the other. Make sure you know that. Down below, this is an exception. This is kind of called the Emin Postulate. We're looking at, not exactly, kind of. Here's an exception to what we just said. This reacts to give a common intermediate. From here you have two different pathways. We can either get the so-called 1,4 product or the 1,2 product. Which one's going to be favored? 1,4 or 1,2? 1,2 product, right?
Yes. Has a lower activation energy for the second reaction.
Because here the activation energy for the 1,2 is actually lower, even though it's a higher energy outcome. This is an exception to what we said above. But you get the right answer here. Here we go. If water is running down the road and it comes to a fork and it can either go this way or this way, which way is it going to go?
Down.
Down.
It's going to go this way. If it goes the other way, let me know. Okay? Here we go. Which way am I going to go? I'm going this way because it's easier. Where do I end up? I end up right here. But the outcome can depend on whether it's controlled by kinetics or thermodynamics. Kinetics is activation energy. Okay? This is largely kinetics. This is thermodynamics. And what I should have been saying earlier is which one's going to be formed first or fastest. First and fastest will be the 1,2 product. If we can achieve thermodynamic conditions, then the most stable is formed. So there's two different things here. Fastest versus most stable. The most stable is not always the fastest. The most stable is not going to be the fastest. We'll look at this handout again during test 3. Right now you need to sort of understand the reaction coordinate diagram. This last question we should be able to answer in about another week. Okay. Back to the model reaction. Which gives off the most heat or energy? Calculation, right? This is your one chance to use your calculator in organic chemistry. All right, so you can get it fired up, change your battery. Okay, there you go. Which reaction is endothermic? Which will occur fastest? Might have to think about that. Are the reactions driven by entropy or not? Okay. Any questions about that? So reaction coordinate diagrams, very important. You'll be asked to draw those in lab reports. You'll see it on tests or whatnot, understanding those. Calculations, and just overall sort of understanding of thermodynamics and kinetics. Any questions about the handout? Got a couple of minutes. Any questions on the DQ page? Which compound can exist in a shear conformation with both alkyl groups equatorial?
C.
B.
Do we get an answer?
B. B.
B as in boy?
Yes.
B, trans 1,2-dimethyl, both equatorial. Put one methyl here. Well, I'm going to do it as if I'm working this problem myself. Could it be A, both equatorial?
No.
I'm going to put that one equatorial. Cis 1,2, 1,2. This to be cis, it should be what? Yes. And they ain't both equatorial. So it ain't A. Trans 1,2. Oh, okay. There we go. Is that trans 1,2? You want to draw in the H's? Does that help? Are those trans?
Yes.
Yes.
Above the H and below.
Well, that is B, and B is both equatorial. Hopefully that's the answer, and we don't have to go any further. Well, the problem is wrong. Do we want to go further? Let's see. Why is C not the answer? Trans 1,3. 1,3 trans, what is this? Would be like that. And they ain't both equatorial, right? And what's the last one?
Cis 1,4.
Cis 1,4. That means it's there, and this is what?
Straight.
Is that cis 1,4?
Yes.
And it ain't equatorial. Only one was. B, boy. Correct?
Yes.
Pretty straightforward. Is there another one you like to do? 11. Cipro can exist in the conformation Cipro. Well, I'll kind of redraw it. The carbonyl there, double bond, all that is, what if I rotate this carboxyl group up so the H of the carboxyl group can sort of hang over there? See, that has free rotation. Unless you want to make an argument that it doesn't. How does that look for a NCI between the H and the O? A intramolecular hydrogen bond? Yeah?
Yeah, so if we were to just show a dashed line from the H to the
Yeah, that's what I
carbon
meant.
middle group,
From what?
in that structure right there, like if we just like put a dash line.
Like this?
No, not that one, the other, or even that one. It would be wrong.
I didn't understand you.
So if, instead of redrawing it to look like the way that you just drew it, and we drew a dashed line on the paper from the H to the other carbon middle, would it be wrong? Or
You
would
mean from here?
Yeah.
Something like that?
Yeah.
That really doesn't illustrate, because that's too far away to make an NCI.
Okay. So
You need to understand that it's going to have to rotate. And if we look at the ring that's formed here, and that's not a covalent bond, but what size ring is here if we count? 1, 2, 3, 4, 5, 6-membered ring? And so this thing is like, okay, whoa, NCI, 6-membered ring. And often you look at that. This H is too far away. So you need to redraw it, so you illustrate it, okay? Did it say illustrate?
and would it like bond, hydrogen bond with the carbon middle group right next to it, or no?
Like right here? Well, let's draw that out. And if we did that, what size ring are we making there?
I was only 4.
That's 4, okay? What do you know about 4-membered rings?
Too much strain.
We're past time here now. It's like this, okay? I can clap right here. Consider this a nice 5, 6-membered ring being formed, okay? On the other hand, if it's shorter, it's like, okay, like this. It's like, there's nothing out here. And I have to, okay. On the other hand, if it was too long, it'd be like, 5 and 6 is perfect. For reaching around and doing an NCI. So I would propose the original one, my 6-membered ring. Okay, guys, Wednesday, please arrive early. We'll be passing the test out at 5 till 7:55, so at 8 o'clock we can begin and everybody's comfortable, okay?
I think it's because he doesn't notice if you skip around.
We'll take